Hands-on with Pandas, creating and exploring data frames. In this lesson, we dive into Pandas basics and intermediate techniques. Explore how to create, manipulate, and analyze tables of data using Python. Running the cell now. What is Pandas? Pandas is a Python library for working with tabular data. It helps you load, clean, explore, and analyze large datasets efficiently. Running the cell now. We prevent distracting warning messages. We prevent distracting warning messages. Next, we import Pandas, a library that helps us handle table-like data in Python. We use the short nickname PD every time we use Pandas. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. This initial code sets up the environment by importing Pandas and numpy, essential for working with tabular data in Python. Although there's no visible output yet, notice that we've also suppressed warnings to keep the workspace clean, preparing us to load, manipulate, and analyze datasets efficiently in the upcoming lessons. This foundation is key to leveraging Pandas for data exploration. Creating your first data frame. A data frame is like a table in Excel, rows and columns with labels. Let us build a simple data frame from scratch. Running the cell now. We create a dictionary with column names and lists of values. Each key is a column, each list is values for that column. These are names of people. These are ages. These are the cities they live in. We convert the dictionary into a data frame, our basic table structure. Let us print the resulting data frame to see what it looks like. Running the cell now. Here, you've created a small data frame with 3 rows and 3 columns, just like a simple table in Excel. Notice how each column has a label, name, age, city, and each row is automatically numbered. This shows how data can be organized clearly, which is the foundation for working with data frames in Pandas. Can you make your own data frame with 3 different columns? Loading real-world data, the Titanic dataset. We often need to load data from an online data file. The Titanic dataset is a classic example for data analysis. Running the cell now. We import Pandas. We load the Titanic dataset from a public GitHub repository. We print its shape and preview the first rows. We print its shape and preview the first rows. We print its shape and preview the first rows. Running the cell now. The output shows that the Titanic dataset contains 891 rows and 12 columns, giving us a sizable, detailed table of passenger data. The first 3 rows preview key columns like passenger ID, survived, P-class, name, sex, and age, highlighting the mix of numerical and categorical variables. This confirms successful data loading from the online source, setting us up to explore passenger demographics and survival outcomes. We want to know what columns are in our dataset. The shape of each column tells us what kind of data we are dealing with. We print this information to get a quick overview. Running the cell now. This output shows the column names and their data types in the Titanic dataset, helping us understand the structure of the data we just loaded. Notice the mix of numeric columns like age and fare alongside categorical columns like sex and embarked, which informs how we might clean and analyze the data further. This step is crucial for familiarizing ourselves with real-world data before diving into deeper analysis. Sometimes, looking at the end of the dataset helps us spot patterns or missing values. We print the last 5 rows for extra context. Running the cell now. This output shows the last 5 rows of the Titanic dataset, giving a snapshot of various passenger details like survival status, class, age, and fare paid. Notice the presence of some missing values in the age and cabin columns, highlighting common real-world data challenges. This peek helps us understand the dataset structure and prepares us for cleaning and analysis steps ahead. Data cleaning, handling missing data. Real-world data is often messy. We must identify and handle missing values before analysis. Running the cell now. It is important to count how many missing values are in each column. Let us print the number of missing entries for each feature. Running the cell now. This output shows the count of missing values in each column, revealing that the age, cabin, and embarked columns have significant missing data. Noticing these gaps is crucial because these are the columns you'll need to address before any reliable analysis, helping ensure your dataset is clean and robust for modeling or insights. Missing ages can confuse our analyses. We remove any passenger row where information about age is missing. We show how many rows remain after this cleaning step. Running the cell now. This output shows that by dropping rows with missing age values, we reduced the dataset from 891 to 714 rows. Notice how this step cleans the data by removing incomplete records, which is crucial to ensure the accuracy of analyses involving the age column. This illustrates the impact of handling missing data on dataset size and quality. Try removing missing values for another column. What do you notice? Sometimes, we do not want to drop rows, just fill in a common value. We find the most frequent port of embarkation. We substitute missing ports with that value. After filling, we verify there are no missing values left for this column. Running the cell now. This output shows that there are now 0 missing values in the embarked column after filling them with the most common port. It confirms that the FILNA method successfully replaced all NANs, which is crucial for ensuring our dataset is complete and ready for analysis without losing records. This step highlights an effective way to handle missing categorical data by imputing the mode. Selecting data, rows and columns. You often want just a part of the table. Pandas makes it easy to access columns or rows with simple labels or positions. Running the cell now. Sometimes, we want one column from the whole data frame. Let us extract all names of Titanic passengers. We show the first 5 names as a quick preview. Running the cell now. Here, we selected the name column from the data frame, which gives us a series of all passenger names. Notice the output shows the first 5 names, confirming we successfully pulled just that single column, focusing on rows by default with .head. This illustrates how easily Pandas lets you isolate and inspect specific data using column labels. We often select rows with specific conditions, like filtering data in Excel. Here we filter for female passengers who are less than 18 years old. Printing 3 key columns helps us quickly check the results. Running the cell now. This output shows a subset of the original dataset, filtered to include only female passengers under 18 years old, demonstrating row selection with multiple conditions. Notice that age and sex columns confirm the filter, with each listed passenger meeting both criteria, highlighting how Pandas can quickly isolate specific groups in a table. This aligns with the lesson's focus on selecting data by row conditions and accessing key columns for review. Sorting and descriptive statistics. Sorting data and getting summary stats help us spot patterns quickly. Running the cell now. Sorting lets us quickly find the youngest passengers. Here, we reorder the dataset by the age column, ascending. We print a few of the youngest names and their ages. Running the cell now. Here we've sorted the dataset by the age column in ascending order, showing the youngest passengers first. Notice the very small age is below 1 year, highlighting infants in the data. This sorting step is crucial for quickly identifying age-related patterns and outliers in the dataset. Descriptive statistics summarize numbers in the dataset. We get quick insights into counts, averages, and ranges for numeric features. Running the cell now. This output shows key summary statistics for each numeric column in the dataset, including counts, means, and quartiles. Notice how the aged column has fewer values, 714, compared to others, 891, indicating missing data, and how FAIR varies widely, from 0 up to over 500. These insights help us understand data distribution and identify columns that may need cleaning or further exploration. Sometimes, we want to know all unique values in a column. We find all the ticket classes in the Titanic data. We also count how many passengers were in each class. Running the cell now. This output shows the unique ticket classes in the dataset, 1, 2, and 3, and their respective counts. Notice that the majority of passengers are in Class 3, which is important for understanding the dataset's demographic distribution. Sorting and counting these classes helps us quickly identify how passenger data is grouped by ticket class, setting the stage for deeper analysis. Grouping and aggregating data. Grouping helps you see big patterns, like survival rates for different groups. Running the cell now. Grouping divides the dataset into custom groups, such as by gender. Here, we compute the fraction of survivors in each gender group. The answer is shown as a percent to 2 decimal places. Running the cell now. This output shows the survival rates for men and women, calculated by grouping the data by sex and taking the mean of the survival column. Notice that about 74.2% of women survived compared to only 18.9% of men, highlighting a significant difference in survival outcomes between these groups. This demonstrates how grouping and aggregating reveal important patterns within categorical data. Try grouping by a different column, like P-class. What pattern do you find? Grouping can help us see how ages vary in different classes. We compute the average age for first, second, and third class passengers. A rounding step makes the output easier to read. Running the cell now. This output shows the average age of passengers grouped by their ticket class, revealing that higher classes tend to have older passengers. Notice how the mean age decreases from first to third class, highlighting how grouping and aggregating can uncover meaningful patterns in the data. This helps us understand demographic differences within each group. Combining columns, creating new features. Sometimes, you need to make new columns by combining or transforming others. Running the cell now. We add a new column to measure the total number of family members per passenger. Family size is siblings, spouses plus parents, children, plus the passenger themselves. We print the result for the first few passengers. Running the cell now. This output shows the new family size column created by adding siblings, spouses, parents, children, plus 1 for the individual themselves. Notice how the counts vary, reflecting different family group sizes, which can be a useful feature for understanding passenger demographics. This demonstrates how combining existing columns can help generate meaningful new data for analysis. Merging data frames, join two tables. Use merging for cases like joining passengers with extra info from another file or dataset. Running the cell now. Make a small example table containing names and their titles. Define a data frame called titles with a dictionary specifying columns. Add the name column with values Alice, Bob, and Charlie. Add the title column with values MS, Mr., and Dr. Merge df_small with the title's data frame on the name column while keeping all rows from df_small. Output the merged data frame to the console. Running the cell now. This output shows the result of merging two tables by the named column, adding that title from the second data frame to the original data. Notice how each row from the first table is enriched with the corresponding title, demonstrating how a left join helps combine related information from separate datasets into one unified view. This is essential for cases where you want to add descriptive data, like titles or categories, to your main dataset. What real-world scenarios could merging support, besides adding titles? Pivot tables, quick summaries by group. Pivot tables quickly summarize data with one line per group. Running the cell now. We create a pivot table summarizing survival rates by ticket class and gender. We print the pivot table rounded to 2 decimal places for readability. Running the cell now. This pivot table shows the average survival rate, survived, broken down by passenger class, P-class, and sex. Notice how survival rates are higher for females across all classes, especially in first class with 97% survival, illustrating how the pivot table quickly summarizes complex group comparisons in one clear view. This highlights the power of pivot tables to reveal key trends in group data with minimal code. Time series, handling dates and plotting trends. The Titanic dataset does not have real dates, so let us try the flights dataset for this. Running the cell now. We import Seaborne. We load the flights dataset containing monthly air travel totals. We print its shape and preview the first rows. We print its shape and preview the first rows. Running the cell now. The output shows the flights dataset has 144 rows and 3 columns, year, month, and passengers. This confirms the dataset's time series structure, with monthly passenger counts over several years. Noticing this shape and columns is key before we proceed to handling dates and plotting trends over time. To work with time series, we create a column of proper date values. We join the year and month together for correct ordering. We sort the table by this new date, and then set it as the index. We plot a line chart to show how passenger numbers change by month. Running the cell now. This plot shows the trend of monthly flight passengers over time, with the date correctly formatted as a date-time index. Notice the seasonal peaks and overall patterns reflecting passenger volume changes throughout the years. This output demonstrates how combining year and month into a date time allows clear time series visualization, essential for analyzing temporal trends. Pandas visualization, quick charts. You can plot right from Pandas to quickly explore patterns. Running the cell now. We plot a histogram to see how ages are distributed among Titanic passengers. Running the cell now. This histogram shows the distribution of the age column in the dataset, revealing how ages are spread across 30 bins. Notice the shape of the curve, which helps identify common age ranges and any potential outliers. This quick plot from Pandas offers an immediate visual summary, making it easier to spot trends without extensive coding. Mini-project, Titanic passenger analysis. Let us use all the skills so far on the Titanic data for a quick analysis. Running the cell now. Time for some hands-on exploration. We ask for a ticket class, so the user can pick which group to study. We filter the dataset down to that ticket class. We print how many people were in that class. Running the cell now. Here, the code filters the Titanic dataset to show only passengers from the chosen ticket class and then counts how many there are. The output tells us that there are 184 passengers in the second class, highlighting how user input controls data subsetting and helps focus analysis on specific groups. This step reinforces filtering data based on conditions, a key skill in analyzing subsets within larger datasets. Now we calculate survival in just that ticket class. Take the mean of the survived column and multiply by 100 for %. Print the answer with 1 decimal point for clarity. Running the cell now. This output shows that about 47.3% of passengers in the selected class survived the Titanic disaster. Notice how calculating the mean of that survived a column directly gives the survival rate as a percentage, which helps us quickly understand the proportion of survivors in that specific group. This reinforces using basic Pandas operations to derive meaningful insights from subsets of data. Next, we find the youngest survivors in our group. We sort by age for those who survived and pick the top 3. This can reveal patterns or special cases in the data. Running the cell now. Here we see the 3 youngest passengers who survived, sorted by age, highlighting that very young children had a high survival rate. This output connects to the intent of filtering survivors within the dataset and ordering them to reveal key demographic insights, in this case, that infants and toddlers were among those saved. Notice the very low ages under 1 year, which emphasizes the importance of age in survival outcomes. Best practices and performance tips. Use .copy to avoid changing the original data by accident. Avoid loops. Most manipulations are faster with built-in Pandas methods. For very big data, use .read_CSV with options like chunk size and dtype. Profile your code with %timate or %time to check for slow spots. Running the cell now. Troubleshooting common Pandas errors. Kira, misspelled or missing column. Check spelling and existence. Setting with copy warning, you probably edited a slice of the data frame. Try using .copy. Dtype warning, data format is not consistent. Specify data types with dtype when loading. Running the cell now. Challenge, can you find the oldest passenger in each ticket class? Plot a bar chart of survived versus not survived for each class? Merge a new table of your own with extra info per person? Pause the video and try one or more. Running the cell now. Recap, what did you learn? Creating and loading data frames. Cleaning, selecting, grouping, joining and visualizing data. Running analyses on real datasets. Building confidence for your own Python data projects. Running the cell now. Thanks for learning Pandas. If you enjoyed this lesson, please like and subscribe for more practical data science videos. Happy coding! Running the cell now.